This presentation will be about inherent safety against cyber attack on process systems. I might add a subtitle to this and call it How to Analyze Cyber Vulnerabilities During a HAZOP, which we'll get to near the end. Brief commercial. Connexus is an independent engineering consulting firm. We're focused on providing services in the for safety instrumented systems, and you can read those there. We also analyze risk associated with process plants using different techniques, including things like HAZOPs and LOPAs. We provide fire and gas mapping services, and including performance target selection, detector placement, and coverage assessments. And our cybersecurity team provides industrial control cybersecurity services from policy and design all the way through to acceptance, compliance, vulnerability assessments, and incident response. We do make a few products. Two of them, Effigy and Vertigo, are available to you if you're interested. Dulcet Analytics is only used internally, and I'll talk about Dulcet in a few minutes in the presentation. Vertigo is an SIS lifecycle tool. You can learn more about it on our website. And Effigy we use to do fire and gas mapping services, and you can learn more about it on our website. We're an ISO 9000 certified company, and we were founded in 2004. Since 2004, our team has analyzed the security and performance of a lot of process control and industrial control networks. We have analyzed a great deal of safety instrumented functions and performed or facilitated a lot of different types of risk analysis for our customers around the world. Our senior staff that you see here are backed up by a junior staff team and are located at our headquarters in Columbus, Ohio, as well as our offices in Houston, Dubai, and Singapore. So into the presentation. So a brief introduction. There's been a lot of money and energy spent to prevent cybersecurity attacks. In the business world, the focus is primarily on protecting data, things like personnel and financial data, designs, trade secrets, things like that. And we use some very powerful tools that are available to just about anybody today, including DMZs or demilitarized zones, which we'll talk about a little bit more later in the presentation. In the operations world, things are just a little bit different than they are in the business world. Our focus is on protecting the process itself, on protecting the equipment, protecting people, and protecting the environment. And we use, though, the same tools. I would argue we use them with a little bit of a caveat that we have to account for things like embedded controllers and the unique characteristics that they have. They're not the server or PC, and they don't have the bandwidth and capability that those do, but they function very well, and they're needed for the things that we use them for. And then there's also critical timing requirements in the operations space that aren't really relevant in the business space. And all those things affect how we use those tools, if you will, for cybersecurity. Technology is awesome. We use technology today to solve a lot of challenges, the microprocessor specifically, and high-speed communications. Unfortunately, last year, some ethical hackers were able to demonstrate that over the internet, through the entertainment system in a vehicle, they were able to take control of some of the vehicle's critical systems, even including the brakes. This is unfortunate. The idea that an automobile manufacturer cross-connected those systems and didn't think too much about it, or at least didn't think enough about it to prove that they couldn't or prevent them from being hacked, is a little disturbing. And so we need to keep that in mind when we're dealing with these systems, that they're not perfect, and the human beings building the software and the firmware for them are not perfect. I'll give you an example of somewhere where we maybe didn't think through something that we all operate every day. So consider the modern car and power windows, not the ones with the cranks on them, not the old lock systems where you could pull the lock. Today, there's a lot of cars where there isn't even a physical lock that you can grab and pull, let alone any type of hand crank. There are kids that are getting licenses today do not know that windows were cranked up and down at one time, which is pretty interesting. However, what bothers me is that when I was 17 years old, I was horsing around on some back roads, and I accidentally drove a 1968 Volkswagen out into the middle of a lake. I was going very fast, and as the Volkswagen was sinking, I was lucky that I had a mechanical lock and was able to open the door or crank down the window And in this case, I did both. But I got out of the vehicle and swam away from it while it was sinking slowly into the lake. That is probably the system on a modern car that will fail when it's submerged in water. And I think this is a place where the automobile manufacturers owe us a responsibility to make sure that there is a way to get out of the vehicle. Fortunately, there are some third-party people that have come up with things like life hammers that if the automobile manufacturer would put them in a vehicle in a safe place that was easily accessible, might prevent having a problem here. So this is just a good example of where technology is really powerful, really capable. We all love it, we like it a lot, but we may not have thought through the problem all the way. So we already rely on technology to solve almost every problem, and we're going to continue to do it because it brings big benefits. So some of the benefits that have been recognized are in the world of operations with programmable controllers or programmable logic controllers, commonly referred to as PLCs, and then the computers that run at L2 and L3 that interact with them. And those systems have been able to significantly improve productivity and quality. And so we're not going to stop using them. They run machines very well. They're very task-oriented. And we can program them to do just about anything we can imagine. And networking them horizontally, in other words, making it so that at L1, the controller PLC can talk to another controller or PLC at level 2, that they can do the same thing. You know, we all know that PLCs talk to the HMI from level 1 to level 2, but integrating them or networking them so that they can talk horizontally to each other adds an additional value, and it allows us to improve things like cost, work in progress inventory, being able to tell what's upstream and coming to me and what I need to adjust my downstream process for, productivity and quality. All these things get improved by that horizontal integration. And now companies are coming along and saying, hey, that's pretty cool. Let's integrate it vertically. In other words, let's get the data that's down in L2 and L3 and L1 and bring it up to L4 and L5. And I will admit that I have seen in the past people, especially at L4, connecting right into L3 or L2 or even L1. And there may be a reason for doing that, but that's probably not a good industrial design. So in the diagram I've demonstrated a red brick firewall. So there's a firewall. As a matter of fact, there's 2 of them in this design. So a good industrial cybersecurity design would actually use 2 separate firewalls. One of them would be designed or would have firmware from one manufacturer, and the other one would be from a different manufacturer. So that if the person writing the firmware made a mistake at company 1, that mistake wouldn't have been made at company 2, hopefully, so that the firewalls would actually protect the transmission of malware down into the operational space, possibly. The DMZ, demilitarized zone, exists. It's just nothing more than a network between the firewalls, if you will. Now, I realize that you can have one firewall, and you can set this network up, or DMZ up, adjacent to that firewall, and that's fine, and functionally it works like the one I'm showing here, but it's one firewall then with one set of firmware. And if the automobile manufacturer couldn't get it right with the entertainment system and some of the drive-by-wire systems in the vehicle, then there's a real good chance that that human being or similar human being programming a firewall somewhere else in the world might make that mistake too, or make a similar mistake and consequently allow bad things to happen. So 2 firewalls is a good idea. And the benefit we get then by integrating vertically is at the site level and at the enterprise level, now we can do more analysis, and we can work on things like workflow and raw material management and stuff like that to control cost and productivity even more for the company across even an entire enterprise globally. So it makes perfect sense to want to do this, and all I would suggest is that you do it very well. There is a trend I don't like. And this is a trend that I've heard some people talking about, and it's basically the convergence of the control systems that are run down at L3, L2, and L1. That those are being converged in some cases, or run a little closer. I'll describe that in just a second, with the safety systems that protect the process and the people and the environment. So this convergence is basically bringing control and safety systems onto common networks, potentially putting the CPU, the embedded controller that makes the control decisions, commonly referred to as a PLC usually, or the safety controller or the safety system, putting them into the same backplane, or potentially, and this one I heard not too long ago, which really bothered me, and I think we need to have a lot more discussion about before we do it, is actually putting them into the same CPU in separate processors. This doesn't make me comfortable. That safety system should probably be isolated and shouldn't be cross-connected, just like in the vehicle, the entertainment system shouldn't have been able to talk to the braking system. So another common thing we hear in the cybersecurity world when we talk to companies is, look, we know it's happened. You guys have done a good job of warning us. We appreciate that. But it's not happened to me. And, while people take cybersecurity seriously, real attacks have occurred, but most of them have been for financial, cash, stuff like that. There is one example that has been overused called Stuxnet. The reason it's been overused is because most companies don't want to raise their hand and say, hey, we've been hacked, unless they have some type of legal or fiduciary responsibility to do so. If you're running a process and you don't have those responsibilities and there is no governmental oversight that's threatening to hammer you if you don't, then if you can fix the problem, you're probably going to fix it and not tell anybody. As a matter of fact, if you run a publicly traded company and your process is hacked and no financial information or personal information is released or medical information or anything like that, in other words, no information was released or compromised that is managed by some type of legal or regulatory organization with the power of law, then you may not be willing to tell the world about it because, quite frankly, it could affect your stock price overnight. And so you have a fiduciary responsibility to your stockholders that you need to balance as the management of a company. I think what we need to do is continue to talk about this because, quite frankly, we need disclosure so that we can learn. And we should be very hesitant to assign blame immediately to somebody who discloses that they've been hacked, even though it is our tendency to want to do that. My big concern is that sooner or later, someone's going to be the new example. You may not be purifying uranium. You might be doing something else. But somebody else is going to be an example, and it'll be big enough that they won't be able to hide it, and news will get out. So let's talk about another scenario that people hesitate with, and that's and I've had people tell me this is, hey, we'll be able to detect it. For instance, a man-in-the-middle attack. We'll be able to detect that that's going on. I'm not that concerned about it. Things will probably slow down if something gets in there and does it. Well, I wanted to show you this because this is some analysis we did with Dulcet Analytics on some lab equipment we have. And basically, we had a PLC, some I/O, and a computer running at L2. And we inserted a laptop between the PLC and the computer that was running at L2. And we actually were able to turn it on and execute code that could manipulate and did manipulate the inputs and outputs that were being read at layer 2 from what was actually going on at layer 1, and then take information at layer 2 before it's transmitted back down to layer 1 and say, hey, we changed it, right? So we had the ability with that laptop to actually alter what layer 1 was saying to layer 2 and what layer 2 was seeing and what layer 2 was saying to layer 1. When we turn that on, something interesting happens. So the reason this graph on the left is here and why we want to talk about it, first of all, you can probably assume by looking at it that when the computer was turned on and when it was turned off, and you would be right, at 60 seconds across the horizontal line, the computer was turned off, and somewhere around 85 to 87 seconds it was turned off. So it was only on about almost 30 seconds. What's interesting is the PLC, I talked about timing earlier in the presentation. The PLC is actually operating and communicating between 10 and 11 milliseconds. It's updating its I/O. That actually is very common. That thing I talked about earlier with timing is very critical in the industrial control world. We can't have a lot of slop. We can't have something that says, hey, I'll talk to you when I get around to it in 3 or 4 seconds. That might be okay in building automation where you adjusted the thermostat and you're waiting for the air conditioning to kick on. It's not okay if you're running an assembly line and trying to run a welder on a robot while you're building a car. So we have these real tight groupings that you see in the vertical column. If you go up the vertical axis at 10 milliseconds to 11 milliseconds, you see a ton of data as it goes across the system. Well, when we turn the computer on, an interesting thing happened. The computer was actually able to process the communications faster than the PLC was. And so the net result was it wasn't slower. The communications are actually somewhere between 0 and 10 milliseconds. And so as far as anything talking to this would be concerned, the I/O or the signals would be updated in plenty of time. And without the right tools and analysis, you can't tell that. So with Dulcet Analytics, I can look at it and say, wow, look at that. That doesn't make any sense at all. The HMI and the historian think everything's fine. However, the data doesn't look right. There's communications that is really erratic. And so you get an idea now that okay, this is interesting, and maybe I won't be able to detect the problem. Here's the really scary thing. It doesn't have to be a laptop plugged in between L1 and L2. As a matter of fact, in the case of Stuxnet, it would appear that it was malware running at layer 2 in this system on the supervisory control that intercepted the communications from layer 1 and told the supervisors or the people sitting there monitoring the supervisory control station that everything at layer 2 was fine, that everything it saw below at layer 1 and layer 0 were fine. In the meantime, the centrifuges were being sped up, oversped, and they were operating at a higher pressure than the vacuum they were supposed to be operating at. And so the net result was the machines, the centrifuges, were degrading rapidly, and the operators saw that everything was fine. And it was malware running at layer 2. You might have this malware on your systems right now and not know it. That's the scary part. So, how do I protect myself if cybersecurity is a lost cause and that malware could actually be there? Well, one of the things we do in the process industry, especially anywhere where we have something called a significant hazard, and we'll try to clarify what that means as we go on, but if you have a significant hazard, then in the United States we have a regulatory agency called OSHA that actually expects us at the beginning and every 5 years to perform something called a HAZOP. And in a HAZOP, we determine what hazards might occur, then we determine the consequences of those and what safeguards are available to prevent or mitigate them and the adequacy of those safeguards to do that. And so this gets done on a regular basis, and I'll walk you through this here in a second. But what I'm going to do here in this presentation is actually propose that maybe during a HAZOP or during a review somewhere in between, if, for instance, if you just did your HAZOPs last year, you don't have to wait 5 years to do this. This actually can be done pretty rapidly. We can come in and do it for you. We can teach you how to do it, or we can facilitate and help you do it. So what I would suggest is that we actually do something called a HAZOP cyber check. And so when you're going through this, you're going to look at the cause and you're going to ask yourself, hey, can that cause actually occur as a result of somebody hacking it? Now here's the bad news. If there's a microprocessor, if it's digital, if it's connected to some type of a network, whether it's wired or wireless, some way, shape, or form, there's a really good chance that it could be attacked, that it could be hacked. All right, so we have to assume that this particular cause, this control loop could be manipulated so that a bad thing happened. What is the bad thing? Well, before I get to item number 4, look at the consequences. The very bottom sentence of the consequences are potential fire and fire or explosion and/or explosion. That's a significant consequence. We don't like things that blow up, so I'm going to refer to the consequences as an explosion from this point on. Now we look at the safeguards and we say, okay, safeguard number 4 is a high pressure shutdown that closes Shared final elements, low-level shutdown. All right, so we can't take credit for it. So it's not what we would call a good safeguard. It's there nonetheless. But here's the really bad news: it's digital. It's controlled by PLC, and quite frankly, it's hackable. Number three, the operator response. This is another safeguard to low-level alarm. This is interesting. So the operator is going to actually go do something based on a low-level alarm. Oh, bad news is the low-level alarm could be hacked. So even though the operator couldn't be hacked, the actual indicator could be. And so consequently, this one's hackable too. That's unfortunate. Okay, how about two? Low level shutdown closes low pressure separator inlet. Oh, bad news. That's controlled by PLC. That's hackable too. And then we get down to safeguard number one, and it's just a relief valve. As a matter of fact, it's such a basic relief valve that there's no electronics. It's just controlled by spring. Somebody went out and calibrated the spring in it so that when it gets to a certain pressure, it actually opens up and it's sized for the gas blow-by. Perfect. This is only hackable, keywords here, this is only hackable if somebody can get physically on your site and adjust the spring. It can't be hacked over a network. It can't be hacked because it has a microprocessor running it. So it can only be hacked if your physical security is poor. And so you can assume that this is safe to a cyber attack. All right, that's fantastic. So the good news is when we're doing cybersecurity audits, we actually look for physical security too. And it's something you got to think about in this particular case. So what's available to me? This is pretty interesting. I have the pressure relief valves we were talking about, mechanical overspeed switches. This is one of my favorite devices. I even had these on a submarine when I lived on a submarine and worked in the engine room on a submarine. So here's a cool thing. We basically use a spring again and centrifugal force to manage a rotating shaft. So we have a shaft that's powered by some prime mover, electricity, steam, whatever it is, it doesn't matter. And it's spinning along. And if for some reason it spins too fast, the spring gives in to centrifugal force and the trigger will slip out of its housing and actually hit the trip switch and actually disengage the prime mover for that shaft. Fantastic. That's an awesome tool. There's no electronics. There's no microprocessor. There are microprocessors in overspeed switches. I'm not suggesting that. I'm suggesting a mechanical overspeed trip that's designed to shut the machine down when something goes very wrong. Check valves. Check valves are very simple devices. Fluid tries to go the wrong way, they shut, and they don't let fluid go the other way. Great device. And then some other ones that are listed here. So how do I identify where cybersecurity safeguard is necessary to protect the process? So let's walk through this. We'll go down through this list. If the device is mechanical, like a hand-operated valve, then it cannot be hacked. Makes sense. However, the indicator might be causing an operator to act, though. The operator might be wanting to open or shut a valve because the indicator says so. The question you have to ask is, are they looking at a sight glass or are they looking at something that could be hacked? If it could be hacked, then I have to assume that that particular function is hackable. If a virtual command from any controller, PLC, embedded controller, a computer, anything of that nature could cause an action, then it can be hacked. As a matter of fact, if we look at the diagram to the right, we have a digital pathway from a sensor, and it's going to operate a valve to the right. Digital, by the way, is code word for hackable from this point forward. So anytime you see the word digital, you have to in your brain say hackable. All right. So here's the cool thing. I've got a digital path. This makes a lot of sense. Your safety system could be designed to use this, and that's all okay. But the problem is it is hackable. So what I might do is I might add a parallel analog path to solve this problem. I can use the same transducer, if you will, but I'm going to bring that signal back through an analog decision-making process to control the valve in addition to the digital one, just in case. Now, The challenge here is, how do you set the thresholds, right? When does the analog one operate versus a digital one? And I would say the analog one should be a safety for the digital one, a backup, if you will. So maybe just outside of its normal parameters, the digital parameters a little bit. So if the digital one would operate on alarm at a high or low level, then you might make the analog one do that plus just a little bit of margin. So that this is designed to be a fail-safe in case you're hacked. It's not designed to be part of your normal safety. It's just designed to be the cybersecurity safeguard, if you will. All right? So, third item down. If a hazardous scenario with significant consequences, remember that's things that go boom. If a hazardous, or that burn, right? But if a hazardous scenario with significant consequences could be affected by a cyber attack, then at least one safeguard pathway cannot be affected by a cybersecurity attack. It's not hackable. If all of your safeguards are hackable, then and you have significant consequences, then you need to find a way to modify that. Some of the things we've been talking about here to actually prevent that problem. And if it's not significant, if it won't blow up, if it won't catch on fire, if it doesn't release a toxic gas, if it's not significant, then it can be protected by standard cybersecurity efforts. I might add, significant might also be financial. Now, this is where it gets a little wonky for a minute, right? This is not something HAZOP typically does, but I would add a caveat here that says a significant, if the cybersecurity hack, if you're hacked and that particular thing, whatever it is, causes a significant financial problem, then you might want to consider that significant and actually find a way to protect it too. All right? Just something else to think about. So we're not proposing neglecting good defense in depth strategy. We wouldn't. We actually believe that for stuff to be safe, it has to be secure. Those two words go together. Safety and security are the same thing. Just like the ISA has a safety and security division, this is one and the same. If it isn't safe, it's not secure. We are proposing that a few simple steps, a few simple questions can actually create a much safer process plant. Even a process plant that'll put you on a much better cybersecurity footing so that you don't have to worry about cybersecurity so much or even ignore it. It can actually be a concern, but it can be a manageable concern. These problems, cybersecurity, hacking, all that kind of stuff, these are engineering problems that we can solve. The cool thing is that in this particular case, many of the safeguards are devices, are things that were created long before computers, and they're capable of circumventing cybersecurity challenges. Hey, I appreciate your time today a lot. Thank you for taking the time to listen to this. If you have any questions at all, you can email our company at info@connexus.com, and someone will read that 5 days a week, Monday through Friday typically, and we'll route it to someone else to handle or answer any questions you have directly, or you can call our switchboard at the number listed. Here's an infographic about our cybersecurity business. Most cybersecurity companies tell you that their standards of operating are things like NERC CIP and ISA 99 or the IEC equivalent. We'll tell you that in the cybersecurity world, we even think about things like ISA 84. This is how we get to a point where we look at a HAZOP and say, you could actually be doing some cybersecurity things here that would make this even safer. So we're ISA 84 and ISA 99 experts in our company. We focus on the areas that you see in the gears with the white center, things like oil and gas, from upstream all the way to downstream. We do fantastic work on platforms, no matter where they are in the world, as well as midstream process and downstream piping and delivery systems. The chemical processing industry is a good side. We're very good at that. We also have a great deal of experience in the manufacturing world. Most of us come from the controls world. I personally have over 30 years experience in the controls world. Be glad to share that with you. My name's Jim McGlone, by the way, if you want to reach out to the company and get a hold of me. Water and wastewater systems, we have a lot of experience there, especially on the control side and the cybersecurity side. We understand that process very well. We've automated many of those systems over the years personally. And in transportation, we do a lot of work in transportation around the world. We're glad to share some of our experiences with you. We maintain a lot of certifications that are not only generic to the IT world, but are actually specific to the industrial world, including things like I'm certified as a global industrial cybersecurity professional, a GICSP. So our guys maintain a lot of different certifications, and we'll be glad to share all those with you in our professional profiles too if you have any questions. Thanks for your time. Appreciate you listening in.